This is an algebra-based physics unit from the New Jersey Center for Teaching and Learning on special relativity. In this unit, we will discuss the following topics: Einstein's postulates, simultaneity, relativity of time, relativity of length, Lorentz transformation, and relativistic momentum and energy. All right, in this first section, we are going to discuss Einstein's postulates. So, in 1905, Einstein had his annus mirabilis, or miraculous year. At the time, he was a not famous 25-year-old, and in that year, he published 4 papers which revolutionized modern physics. One of those papers was on the electrodynamics of moving bodies. This paper introduced the world to a new field of physics known as special relativity that explained physics phenomena at velocities close or equal to the speed of light. The foundation of special relativity relies on 2 postulates. Here's the first postulate. It's also known as the principle of relativity, and it states, the laws of physics are the same in every inertial frame of reference. Now, it's important to know what is an inertial frame of reference. Inertial reference frames are reference frames that are not accelerating. So, the reference frame is not experiencing any net force. There is an excellent video here from 1960 on frames of reference. If you have access to clicking on it to view it, I would highly recommend it. We're going to look in the next couple of slides at what these inertial reference frames are and aren't for more information. So let's look at this first postulate a little more closely. So here's an example of a bus moving past a stationary observer. So the observer's at rest. The bus is moving toward it at a constant velocity. So that's important, right? Because an inertial reference frame is one that is not accelerating. So not speeding up, not slowing down, not changing direction. So the bus and the observer are in inertial reference systems because they are not accelerating. From the stationary observer's perspective, the bus moves forward with a velocity v. From the perspective of the person on the bus, the observer is approaching the bus with a velocity of v, or this person will be moving toward the bus with a velocity of v, while the person is observing from inside the bus. Einstein's first postulate states that both observers are correct in their observations, since they are both in inertial reference systems and rely on the same laws of physics in regards to how velocity vectors sum. So this postulate that tells us that the same laws of physics apply in all inertial reference frames applies for all inertial reference frames. So in this example, if I move the magnet toward the stationary coil, I get a voltage in the coil of wire. This is inertial reference frame, right? If it's moving at a constant velocity, it's not accelerating. But I also get the voltage in the coil of wire if I move the wire toward the magnet. So from the perspective of the magnet at rest, if the wire moves toward it, I also get a voltage in the wire. Okay, so regardless of whether it's the magnet that moves toward the coil or the coil that moves toward the magnet, we still get the voltage in the wire. So the laws of physics that determine the voltage in the wire apply in both cases because both are inertial reference frames. Here's the second postulate. Einstein realized that his principle of relativity that we discussed in the first postulate applied to Maxwell's equations of electromagnetic radiation as well. those equations are used to derive the speed of light. That derivation is complex and not necessary here. Here we can just say that Einstein's second postulate states that the speed of light in a vacuum is the same in all inertial reference frames and is independent of the motion of the source. All right, so let's look at this a little more closely. Suppose a rocket, right here we have a rocket moving at 1,000 meters per second, launches a missile forward at a speed of 5,000 meters per second with respect to the rocket. So you can see this vector is 5 times the length of the first. Okay. An observer on Earth watching the launch would measure the missile's speed to be 6,000 meters per second because it was launched out of the moving rocket. This is what we learned in classical mechanics. If the same rocket moving 1,000 meters per second sent out a light pulse, so traveling at the speed of light, the rocket would observe the light pulse traveling away from it at the speed of light, 3 times 10 to the 8th meters per second. Einstein's second postulate says that an observer on Earth would also observe the speed of light pulse as 3 times 10 to the 8th meters per second. So, classical mechanics states that an observer on Earth would measure the speed of light pulse as the sum of these two vectors, 3 times 10 to the 8th meters per second plus 1,000 meters per second, which is incorrect. What Einstein's second postulate says is that the speed of light is invariant. It does not matter what reference frame the observer is in. Light will always be observed traveling at 3 times 10 to the 8th meters per second in a vacuum. The effective speed of light through other media is less due to the media absorbing and re-emitting light waves. So the speed of light in air or the speed of light in, other medium may not be 3 times 10 to the 8, but that's because it's being absorbed and re-emitted. So don't worry about classical mechanics, all that mechanics you learned being wrong. We will see that using classical mechanics is still a good option for slow-moving objects. But that starts to break down, that understanding of classical mechanics starts to break down. We're talking about these very fast-moving, like light waves. Okay, so here's a thought experiment. What would you see if you were traveling at the speed of light? If you were moving at the speed of light, the light reflecting off your eyes would move away from you at the speed of light. A stationary observer watching you move past would also measure the light reflecting off your eyes moving at the speed of light. But if you were traveling at the speed of light, both you and the light would appear to be in the same location, since you would both be moving at the same speed. How can the light move away from you in your perspective and be in the same place from the observer's perspective? This violates Einstein's first postulate because you're both in inertial reference frames, so we shouldn't get this conflict here, right? And so the implication is that nothing other than light can move at the speed of light. So you can't move at the speed of light because to do so would violate Einstein's first postulate.